Bismillah Rahman Rahim. Assalamu alaikum. Today we are going to cover another topic from the field of the numerical methods, and today's lecture is basically the continuation of the previous lecture. If you have gone through the previous lecture, so there we have covered the two topics. One of them was the Euler's method and the second was the improved Euler's method. So in our today's lecture, we shall be covering the third aspect of the Euler's method under the title of the modified Euler's method. What is this method? First of all, we shall be developing the formula for this modified Euler's method, and at the end, as usual, we shall be applying it in order to solve few questions. So let's take start. The title of the method is modified Euler's method. Here we are given a differential equation of the form dy over dx. This is the general form of the differential equation along with the initial conditions x0 is equals to y0. So this is the differential equation we are going to tackle. This is basically the first order linear equation, a linear differential equation along with the initial conditions. So we can call it as the initial value problem. Now, in order to approximate the solution of this differential equation under the title of the modified, let me construct here a graph. This is the graph, basically the solution curve of this differential equation within the one interval, the first interval I must say, in between the coordinates say x0 to x1. And we are going to approximate this solution curve by drawing the tangent line at the point, if I call this as the point A, and the y coordinate of this point as y0, so the point of A will have coordinates x0 and y0. And similarly, this is 1 here, corresponding to this coordinate x1, the value y1, if I call this as the point B, having coordinates x1 and y1. So first we draw here a tangent line like this, and the tangent line is at the point A. In order to write down this tangent line's equation, if I call it as AL is the tangent line at the point A, then in order to write the equation of this tangent line, we require the two information. First, we require the slope, and second, we require at least one point on the line. So the point which I am going to use is A. The slope can be obtained by using this differential equation. So here at the point x0 and y0, the slope of AL will be dy over dx at the point x0 and y0 will be equals to x0 and y0. So we can write down the equation of the tangent line AL, and that can be written by writing y minus y0 is equals to slope times x minus x0. So this is the equation of the tangent line at the point A having coordinates x0 and y0. Now after this, we can simplify it by writing it as y0 plus x minus x0 f of x0 and y0. Next, from here to the next place x1, we are giving an increment of h units. So this is the h unit increments in moving from point x0 to x1. If I take the midpoint of this interval, and the midpoint can be obtained very simple just by giving a half increment, means h by 2, so we'll be at the midpoint. corresponding to midpoint, this midpoint, if I draw a line exactly on this tangent line, so there will be a point where this line is going to meet AL. So this point we can call it as P. If I label the y coordinate of this line as y1, 1, so the point P will be having coordinates. The x coordinate will be x0 plus h by 2 and y coordinates will be y11. And of course this y11 is different from this y1. And now you can see here the point P is lying on this tangent line AL, whose equation is written here. And when this point is lying on AL, it must satisfy this equation. So whenever I substitute this point over here, the equation takes the form y11 is equals to y0 plus x0 plus h by 2 in place of x, the x coordinate, minus x0, f of x0 and y0. So these two can be dropped down and the net result takes the form y11 is equals to y0 plus h by 2 times f of x0 and y0. So this is the value of y11 which is at this place of the tangent line. Now I have to use this equation in the derivation of the modified Euler's formula. So I keep it and then we proceed. Okay, I write it here separately. y11 is equals to y0 plus h by 2 into f of x0 and y0. I have to use this equation. Now we proceed to construct the formula. Here we have taken the midpoint, this one. Now we are going to draw a tangent line at this point P, and we can call it as PM. PM is the tangent line at the point P. So the point, the tangent line at the point P will have some slope, and the slope can be written by, because the point P having coordinate these, and we can use again the differential equation dy over dx fxy. This is the starting differential equation. Now at this point P, at P, the slope of the tangent line through P will be equals to dy over dx is equals to f of x0 plus h by 2 and y11. So this is the slope of the tangent line at the point P, which I have shown by PM. Now we draw another line through the point A and going like this. And we assume this line is parallel to PM. If this line AB is parallel to PM, so the AB will have the same slope as that of PM. So this slope will also be the slope of AB if it is parallel to PM. Therefore, we can write down here the slope of AB is equals to, in the form of x0 plus h by 2 and y11. So this is the slope of the line starting from A and going through and passing through the point B. Now, if we want to write down the equation of the line AB, we can use this slope and the point A. So the equation takes the form y minus y0 is equals to slope y11 times x minus x0. This is the point line formation, a point slope line formation. Here we are now going to simplify this result to write in the form y is equals to y0. If I take this before the slope, x minus x0, f of x0 plus h by 2 and y11. So this is the equation of the line starting from point A and is going in this direction. Now, as you can see, the